Hello! In this video we're going to be talking about how to interface the Quickrun 1080 to an Arduino using the pulse width modulation shield that's manufactured by Adafruit. Let's get into some of the details here. So first off, I want you guys to take a look at the Quickrun unit itself. This is designed for remote control cars and trucks, and it's got some great features to it. It can spit out a lot of amperage. It's able to control large size motors. I have to look at the specs. I want to say it's something like 30 or 40 amps that it can provide. We happen to have a bunch of these laying around, so I'm going to use it in a project today with the Arduino. So let's get into some of the details on how we're going to do that. Here's the schematic that we have again. And you can see in here that we've got the Arduino with a pulse width modulation shield from Adafruit. That's already wired up, and it's connected to our Quickrun motor controller here. And it's interesting that this particular Adafruit PWM Shield requires a 5-volt signal, but it typically comes from these pins. With the battery elimination circuit that's included with the Quickrun, it can actually power this up, and through these headers it can power multiple things. So I have it kind of drawn off to the side here, but it's actually going to connect to these 3 pins. Will be connected to our input signal, and that the power and ground will power up the Adafruit PWM Shield. Other than that, we just got it connected to a gear motor, and the other thing that we're going to be using today is a little 10k ohm resistor connected to analog input 0, just to give us a variable input that we can play around with. So as I mentioned, that battery elimination circuit is designed to power up a servo motor on an RC truck. So it'll send out 5 volts through the positive negative connections through there, and that's enough it'll power up our PWM Shield on the Arduino. That works out pretty darn slick. So here's the PWM Shield from Arduino. A couple of details about it. It's got a bunch of input-output pins on it. They're accessible with the header that you install. It's got the analog inputs. That's great. These are the things of interest, though. This allows us to run up to 16 servo motors on this, and if I added another one of these shields to it, it's expandable, so we could add a different address by soldering some different connections here, thus giving it a different I2C address. So let's chat a little bit about the pulse width modulation component here. You know, a digital device doesn't do a great job of sending out an analog or a variable voltage signal. And one way to do that is to use what's called pulse width modulation, where you're snapping on and off a digital output, so to its high and low levels here, and you get kind of a resulting average voltage. So in this example, if I had 50% duty cycle, you'd see that I've got half of the time it's at 5 volts, half of the time it's at 0 volts. The average across there would be a 2.5 volts, so half of the voltage, because it's only on half of the time. Now with some filters and capacitors, you can get that to smooth out and represent a nice 2.5 volt output signal, so you can go anywhere in between your levels of 0 and 5 volts. So these are showing just a couple of the duty cycles. Well, how that factors into our servos is a little bit different, and we need to have a different conversation. We need to talk about the frequency. Our servo motors need to have a signal that's running at about 50 hertz. And so about every 20 milliseconds, we're going to get a new pulse. And what servos are really interested in is the pulse width, right up there. In this case, that's 5 milliseconds, well, at a 25% duty cycle. Not the signal we need for a servo motor. And the servo motors are the same as this Quickrun in terms of the signals that it requires. So here's an example where the servo motors work best when they get a 1 to 2 millisecond signal, and depending on the servo, that might expand to 0.5 milliseconds. That would be at 0 degrees, and 1.5 milliseconds puts it at the 90 degrees. And if you give it a 2.5 or a 2 millisecond, it may move the servo arm all the way to 180 degrees. So when we're setting this up in the code, we have to do a little bit of math and figure out the PWM Shield is giving us numbers between 0 and 4096. So we need to scale that based on the proportions. These are the numbers I came up with in a little bit of testing. They seem to work pretty darn good. So in order to give it that appropriate signal, if I fed it a signal of like this code here, PWM set PWM 00314, that's going to be about at that middle range, setting the servo arm to its 90-degree position. Now when it comes to the hobby servos, that's great. That's the kind of signal that we'd get, and it's the same thing we'd be getting from a radio controller transmitter that's using the standard analog signals. So like a Turnigy, flight controller, or a RC truck transmitter receiver. The receiver unit is going to be spitting out these various 1 to 2 millisecond signals. When it comes to using this Quickrun in this example, well, it's the same signals, but the motor behavior is going to be different. When it's in that mid-range, we're sending it a 1500 microsecond or a 1.5 millisecond signal. That's the signal for the motor to stop. And that's what they call like the neutral stick. So when you let go of the throttle and the springs kick it back to its neutral position, it needs to have that neutral position in order for it to start up. Now, if you go to either side of that, it's going to be forward or reverse action. And it's a proportional response. So the further we send the numbers down from our 314, which seems to be about the center point, giving us a 1500 microsecond signal, the motor will be in a stop position. Go lower than that, it'll move in reverse. Higher than that, it'll move in a forward direction. But these are the constraints that we want to have inside of this. So now I'm taking a look at the Arduino code that's set up for this. We do need to make sure that we've gone up here and installed the right library. So we got to go to include libraries, and I think the one we're looking for is the Adafruit PWM. All right. So I've already got this library installed. It's good to go, but that's one that you're going to have to make this code work. Okay. So, I look into the code itself. I did put the values that I had here for controlling a motor to get the PWM values the correct way. So those numbers are included in here. It's about the range we want to be shooting for with these PWM signals. So out of default, we've got to have a couple of includes for the wire.h so it can talk I2C. We've got to have the Adafruit PWM servo driver in there, so make sure those are included. And we got to tell it to get started up. So I've got a couple other odds and ends in here that just printing some things on the serial monitor, setting the oscillator frequency, and I've run this with and without. It didn't seem to make a huge difference in the results I was getting. And you do need to have this PWM.begin. Back to our other part, we were talking that it had to have a PWM frequency of 50 Hertz. That's what servo motors are looking for. So every 50 milliseconds, we're going to send another pulse. And then in my example, I've got a couple other odds and ends set up, but the ones for the Quickrun are right here. I'm going to send out a signal that says turn off the gear motor. This is the 314. That's its neutral stick position if you're thinking about an RC transmitter. And then I've got to sit there and wait. I've got to wait for that RC transmitter to see that it's in a neutral position. This is a safety feature that if you had a transmitter that was running and the stick was all the way forward and you powered it up and your RC truck is just going to take off flying, it's a safety option that's built into it. In order for the controller to safely power up, it needs to see that it's getting a neutral position. So somewhere in that stopped PWM signal, 1.5 millisecond is what we're really aiming for. That's back to these numbers. It's got to see that neutral position for a while. And I found that 3 seconds is a good time for it to recognize, oh, I'm in that neutral position and we're good to go. Now, I've got a couple other details in here, but the main chunk of the code is in our void loop here. So I'm going to read that analog input, the potentiometer on pin A0, and then I'm going to map that from its raw values of 0 to a 1024, which is the standard 10-bit analog digital conversion. And I need to map it between our numbers of 111 to 491, and that goes back into this table, you know, the 111 to 491. That's the range that a little bit of research produced that would give me the right PWM signal length needed. Then, just for fun, I'm going to print that information out on the serial monitor and then send that off to pin number 8 over to the motor speed. So at this point, I've got it all wired up for you, and there's a couple other details in here that we're not going to be overly concerned about, but per the schematic, I've got my battery that's feeding the Quickrun controller. There's the on-off switch over here for the Quickrun, and that's going to pin number 8 on the PWM Shield. The other thing I've got that's important based on our sketch today is this potentiometer that's hooked up to analog input pin 0. So what we're going to do is to get this powered up and running and execute the code. So I'm going to go back to this here for a second. On the code, we're going to go ahead and upload that code into the Arduino. And then I'm going to open up the serial monitor. So we had success. Serial monitor is launching. And there we go. I can see the numbers that I'm getting. And as I rotate the potentiometer, the numbers are changing. And they're going to those minimum and maximum 111 down to 491-ish. Okay, so I'm going to leave it intentionally off a little bit. And we're going to go back to taking a look at the Quickrun motor controller. Okay, now I've not powered this up. There's a couple things you're going to see when I power up the Quickrun motor controller. There should be another LED over here, a green one that pops up. That's basically that battery elimination circuit pushing the voltage from the Quickrun. It supplies 5 volts to this PWM Shield. Okay, so I'm going to go ahead and click this button to fire that up. And you can see I've got a green light that popped up over here on the shield. And then this Quickrun has got a blinking light over here. Now, the blinking light tells me that the Quickrun is not in the signal it's getting is not in that neutral position. So it's not actually going to fire up the motor. This is that safety option that we're talking about. So with the code running here, right now I'm sending in a signal that's in that 375 range. So, if you go back to the Arduino right here, we're sending it 375, and the range that we're looking for, I'll go back up to this table here. We want to see 111 to 491, with 314 being about in that neutral position, neutral stick. So I'm going to continue to rotate the potentiometer and take a look at that blinking light. All right, it got to a certain point. Now I got the potentiometer moved into that 300 range, and then all of a sudden it took off nicely. So it's running quite well. What this means is that we have a little bit of a startup problem. So as I rotate this, it's basically feeding it the 1 to 2 millisecond servo signal range from the shield to the Quickrun. That's powering up the motor. And once I get it in that middle range, you can see the Quickrun LED goes to an off position. It starts blinking once you get it on one side of it, and it becomes solid, or pretty close to solid when it's maxed out, I believe. Yeah, there we go. So a couple of things I just wanted to say that back to our code, it's important that we feed information to it in this way. For startup purposes, what this will do is to send that PWM at the mid position, let it dwell for 3 seconds. So that light would have turned off if I would have powered this up first and then run the program or hit the reset button on the controller. So there we go. That's a demo of using the Quickrun with the Arduino PWM Shield, and everything seems to be working pretty slick. So hopefully that helps you guys with your projects, and we'll catch you next time.